in this problem, we need to verify the symmetrics for the given polar equations. The equations has a slightly different format that we have in class. In general, the equation could be written as r as a function of theta. However, here, the polar equation is given by r squared equal to cosine of 2 theta. Right? If we wanted to solve r, we need to take the square root, and then we also need to take into account the positive or negativeness of the square root. Okay, so indeed, we can actually avoid this process. All right, on the right hand side, this is the pictures that we had already knew. Suppose we are given a polar coordinate r and theta, which appears on the first quadrant. Now we can obtain the three important symmetric points, right? I mean, for example, r and negative theta. This point is a symmetric point with respect to the x-axis. All right. In general, when we verify the symmetries, like part A, we wanted to verify r theta equal to r of negative theta. But because of the special structure of the polar equation here, we want to avoid solving r. Okay, so we need to interpret this one slightly differently. For example, we can say if r theta is on the graph, then r or r negative theta is also on the graph. If we can verify this, then this just means the polar graph is actually symmetric with respect to the x-axis. Right? So this is our basic assumptions. R squared equal to cosine 2 theta. This is simply tell us r theta is on the graph. Now, what about r and the negative theta? Then this is just the property of the cosine function. Cosine 2 theta and the cosine negative 2 theta, they are exactly the same because cosine is an even function. All right. So the second block here tells us r negative theta is also on the graph, and this is exactly what we wanted to prove. Okay, so this is part A. Part B, similarly, right? We wanted to verify if r theta is on a graph, then negative r theta will also be on the graph, right? As we can see here. Okay, so let's just try to calculate the square term of negative r. Obviously, this will be the same as r squared. Then of course, that will be cosine 2 theta. Okay, so the second equation tells us negative r theta is also on the graph, and we'll finish the proof. The part C, where we can argue in different ways. For example, from part A and B, we already knew the symmetric with respect to the x-axis and then the origin. All right, so somehow it looks like in this one, right? We have the symmetry in this direction, and then also we have the symmetry in this direction. Then automatically it will guarantee the symmetries, right, in the y direction. All right, we can break this one into the two-step procedure. For example, first obtain a symmetric point with respect to origin, and then do the symmetric with respect to the x-axis, and then we can obtain that point. Okay, so this is one way. Another way is we can verify directly. That means if r theta is on the graph, then r pi minus theta should also be on the graph. Okay, so let's verify this. This is a starting point. The next one, we utilize the property of the cosine function, right? 2 pi minus this one is the same as cosine 2 theta. So here we also utilize the properties of the cosine function. That is, the period is 2 pi. Okay, and then just a little bit algebra, it will tell us that r pi minus theta should also be on the graph. Okay, so this is a straightforward verification in part C. All right, thanks for watching.